Welcome everyone. So I'm going to present you the DARTS concept, so differentiable architecture search model for neural networks. So let's consider in our neural network we have two nodes at the beginning, one node I and one node j, and we don't know which operation we should apply to node I. We have a set of candidate operation made of three operations, and the first thing we're going to do in DARTS is to replace this edge with a question mark by a super edge made of parallel edges. So three edges in parallel, one for each operation. Each edge is weighted by a real number, alpha. And then the output of the super edge is basically the weighted sum of the output of the three operations associated with each edge. And how do we weight each operation? We basically take the softmax over the alpha so that we get a probability distribution, and the sum of the weights sum to 1. Okay, those alpha are learnable parameters, and they're going to learn basically the architecture. How do we optimize them? Well, quite simple. Since we are looking for the architecture, we want to minimize over alpha the validation loss. That is parameterized by alpha the architecture and a function W that is basically all the weights of the network. So keep in mind that the operation, the candidate operation, can be parameterized by some weights, and those W star are basically the W star that minimizes the training loss for a given alpha. Okay, so we solve this bi-level optimization problem, and we end up with some alpha and some W star. But then we basically need to select which operation we want, and we're going to do this based on the alpha. We're going to basically prune the edge by retaining the operation with the highest alpha. So basically we take the argmax over the set of operation candidates. So why do we take the argmax? Simply to limit the gap between the super edge and the single edge. Okay, so we had only two nodes in our network. Now let's switch to a network where we have more nodes. So here, for example, we have a cell where we have three nodes, 1, 2, and 3. First, notice the structure of the network. Each node is connected to all the previous nodes except the input. So as you can see, 3 is connected to 2 and 1, 2 is connected to 1. This is basically what reflects this formula here. Then we have 4 different edges, and for each edge we don't know which operation we should perform. What is the best one for the architecture? So for this, first we introduce a search space that is made of 3 operations: skip connection, convolution 3 times 3, and average pooling 3 times 3. Okay, then as we did before, we're going to replace each edge by 3 edges in parallel, one for each candidate operation. Then we're going to weight the output of each edge with some alphas where we apply the softmax. And then we are ready to basically optimize both the architecture and the weights of the network. So to do this, we're going to use an alternating step procedure where first we find the optimal weights while freezing the architecture, so freezing the alphas, and then we update the architecture while freezing the weights. So we update the alphas. And those two steps are performed using gradient descent, and this is basically the strength of DARTS, that first we are searching for all the architecture at the same time, and secondly that we can use gradient descent to do this. So we alternate between those two steps until we converge to a minimum, and once we reach that minimum, basically we're ready to print the network. So we're gonna output the optimal architecture by retaining only connection with the highest weights. So basically connection with the highest alpha. And so as you can see, from input to 1 we selected convolution 3 times 3. From 1 to 2 we selected average pooling 3 times 3, and so on. Okay, so this is just a simple introduction to DARTS. If you want to know more, feel free to look at the paper or look at my website. Thank you.